All right, let's dive right into this explainer. Today, we're unraveling the invisible tug-of-war of chemical reactions that is literally happening all around us. You know, when you look at a chemical equation on a piece of paper, it kind of looks static, right? Like a totally settled fact. But in reality, inside that beaker or that massive industrial reactor, it is a dynamic, constant battle. We're going to master the hidden levers that control this battle, specifically temperature and pressure. We'll break down exactly how they influence both the rate of a reaction and the ultimate position of chemical equilibrium.
So why is this so absolutely crucial? Well, because this exact topic is the pain point that costs students massive exam marks every single year. The fundamental difference between how fast a reaction happens and how far it goes before it balances out, it's incredibly easy to mix up. But by the end of this explainer, you're going to have a rock-solid visual framework to untangle these concepts permanently. No more second-guessing on test day.
Okay, here's our survival guide for today. We'll start with the reaction rate rules, then shifting the equilibrium, move into exothermic versus endothermic reactions, the gas moles factor, compare rate and equilibrium head-to-head, and finally, look at avoiding common exam traps.
Section 1. The reaction rate rules.
When we're talking about rate, everything is about speed. We're talking kinetic energy and particles violently smashing together. Let's look at the two main levers we can pull here. First up, increasing the temperature. This means we're giving the particles a massive kinetic energy boost. They're zipping around way faster, and critically, a lot more of those particles now have energy that exceeds the activation energy. That's the minimum energy required to actually trigger the reaction. Now, the second lever is pressure. And keep in mind, this applies strictly to gases. When you crank up the pressure, you are physically squeezing those gas particles closer together into a much tighter space.
So, by pumping in energy through heat, or squishing them together through pressure, you obviously increase the frequency of collisions. But, and this is huge, frequency isn't the whole story. The ultimate result here is a greater proportion of successful collisions. Remember, way more particles are now blowing past that activation energy barrier. It's not just about bumping into each other more often, it's about slamming together with enough force to actually spark a reaction.
Section 2. Shifting the equilibria.
All right, let's switch gears. We're completely shifting our focus away from speed now and looking at the final state of balance. When dealing with equilibrium, temperature is actually the single most important factor. Why? Because it's literally the only thing that changes the equilibrium constant, or Kc. The golden rule you gotta remember is that the system's entire goal is to oppose whatever change you make to it. So, if you heat things up, the system is gonna shift to absorb that added heat. It basically just wants to cool itself back down.
Section 3. Exothermic versus endothermic. To really wrap our heads around how a system absorbs or releases heat, we've got to look at exothermic reactions first. In these reactions, the change in enthalpy, or delta H, is negative. The absolute easiest way to visualize this, and to never ever get confused on a test, is to imagine heat essentially acting as a product. The reaction happens and boom, it spits out heat into the environment right alongside the chemical products.
By mentally treating heat as a product, the equilibrium shift becomes totally logical. If we crank up the temperature, we are essentially dumping way more product into the system. To absorb that excess heat and get back to balance, the system has to run in reverse. It shifts to the left, toward the reactants. Conversely, if we cool the system down by dropping the temperature, we're taking away that heat product, so the system shifts to the right to replace it and generate more heat.
On the flip side, we have endothermic reactions. Here, the delta H is positive, meaning heat is literally required for the reaction to even happen. So you should think of heat acting as a vital reactant entering the system, sitting right there on the left side of your chemical equation. The crucial takeaway here is that raising the temperature in an endothermic reaction is basically like adding more of a vital reactant. The system is like, awesome, I've got more fuel, and it shifts right towards the products to consume that extra heat. And naturally, cooling it down starves the reaction of the heat it desperately needs, which pushes the balance right back to the left.
Section 4. The gas moles factor.
Okay, let's talk about how pressure messes with these delicate balancing acts. And again, remember, this only plays a role in gaseous equilibria. The rule for pressure is wonderfully straightforward. It's entirely a counting game. You just count the moles of gas on each side of the equation. If you increase the pressure, the system feels squeezed. To relieve that pressure, it shifts towards the side that takes up less physical space, the side with fewer moles of gas. If you decrease the pressure, giving the system more room to breathe, it shifts to the side with more moles of gas.
Let's look at a classic chemical example to see this in action.
On the left side of our equation, we've got 1 mole of nitrogen gas and 3 moles of hydrogen gas. That gives us a grand total of 4 moles of gas. Over on the right side, we produce 2 moles of ammonia gas. So 4 moles on the left, 2 moles on the right. If we crank up the pressure on the system, it has to shift to the right, toward the ammonia. Why? Because 2 moles take up way less space than 4. It's just nature's way of relieving the squeeze.
Section 5. Rate versus equilibrium compared.
So we've explored speed and balance totally separately. Now it's time for the ultimate showdown, comparing them directly. You'll see that temperature is the universal lever. A bump in temperature will always increase the rate of reaction, and it will always change the equilibrium position and the Kc value depending on if it's exothermic or endothermic. Pressure, though, pressure is super picky. It only increases the rate for gases, and it only shifts the equilibrium if the number of gas moles actually differs between the left and right sides. Actually, if the moles are equal on both sides, changing the pressure won't shift the equilibrium at all.
Section 6. Avoiding common exam traps.
Let's wrap this up with a rapid-fire survival guide, because this is exactly where people hemorrhage marks on exams. First off, just writing more collisions is not going to cut it. You must explicitly write more successful collisions to secure that point. Second, do not forget that pressure only applies to gases. Don't go talking about pressure if you're dealing with aqueous solutions. Third, don't give a rate answer to an equilibrium question or vice versa. Always stop and ask yourself, am I talking about speed right now or balance? And finally, for any pressure equilibrium question, you absolutely must explicitly mention the moles of gas on both sides to back up your answer.
So, what should you actually take away from this whole explainer? Burn this simple one-line summary into your brain. Temperature changes everything, both the rate and the equilibrium. But pressure has super strict rules. It only cares about gases, and for equilibrium, it only cares if there is a literal difference in the moles of gas. Understanding this stuff isn't just about passing an exam, right? It's really about understanding how we as humans manipulate nature. Think about it. Now that you understand the hidden levers of temperature and pressure, consider this. If tweaking this chemical balancing act allows us to create fertilizers, synthesize life-saving medicines, and generate fuels efficiently, what else in the universe could you engineer if you fully master these rules? Keep questioning, keep learning, and I'll catch